In January 1961, a U.S. Air Force B-52 Stratofortress broke apart over North Carolina, carrying two Mark 39 hydrogen bombs weighing 4 tons each. The aircraft, on airborne alert during the height of Cold War tension, suffered a catastrophic structural failure caused by a fuel leak near its right wing. Eyewitnesses saw fire streaking across the sky as the plane disintegrated, scattering debris, crew, and nuclear weapons over farmland near the town of Goldsboro. Each Mark 39 bomb had a yield of 3.8 megatons, over 250 times the destructive power of Hiroshima, capable of erasing the entire eastern seaboard. As the aircraft broke apart, one bomb's parachute deployed correctly, slowing its descent. The second plummeted into a swamp, burying itself more than 20 feet deep. The arming mechanisms in both weapons activated during free fall. 5 of 6 safety devices failed on one bomb, leaving only a single low-voltage switch preventing detonation. That fragile component, later described as a cheap electrical switch, stood between the United States and the most devastating accidental explosion in history. Investigators recovered the parachuted bomb nearly intact, its casing embedded in mud. Inside, arming rotors and power lines had advanced into armed position. The second bomb proved unrecoverable, excavation filled with water, and radiation readings indicated the uranium secondary remained buried deep in the ground. To secure the area, the government purchased the farmland and sealed it under perpetual easement, marking the coordinates with a simple warning sign. Declassified reports later confirmed that both bombs reached full pre-detonation sequence, halted only by an unbroken electrical contact measuring less than a centimeter wide. Had the connection completed, a nuclear blast would have vaporized Goldsboro, sending fallout north to Washington and beyond under winter winds. For decades, officials downplayed the danger. Internal memos in 1963 described the event as a near detonation of unprecedented magnitude. In 2013, Freedom of Information Act releases exposed the technical truth. America had come one step from destroying itself with its own weapon. The Goldsboro Incident joined a classified list of broken arrow events, military code for nuclear accidents not involving deliberate launch. Between 1950 and 1980, the United States recorded at least 32 such incidents. Bombs lost, dropped, burned, or damaged during transport and maintenance. One of the earliest occurred on February 13, 1950, when a B-36 bomber jettisoned a Mark IV bomb into the Pacific after engine failure near British Columbia. The weapon, containing depleted uranium and conventional explosives, detonated on impact, scattering radioactive debris across snow-covered mountains. 5 years later, a similar loss unfolded off the coast of Georgia. A B-47 collided midair, releasing a 7,600-pound nuclear bomb into the Tybee Sound. Recovery teams searched for months, dragging sonar equipment across the seabed, but the bomb, later described as potentially complete, was never found. Locals still refer to it as the Tybee bomb, a silent relic buried under sand and silt, location uncertain even today. January 1966, over Palomares, Spain. Another B-52 collided with a refueling tanker, scattering 4 hydrogen bombs. 2 exploded conventionally, releasing plutonium dust. Spanish farmers watched metallic parachutes drift down. Cleanup crews scraped hundreds of tons of contaminated soil and shipped it back to South Carolina. A 4th bomb plunged into the Mediterranean Sea, recovered after an 80-day underwater search that involved submarines and sonar triangulation. Each incident revealed the same truth: safety systems built for war could fail during routine operations, and every safeguard carried its own blind spot. Engineers documented melted wires, faulty relays, and improper handling procedures, converting tragedies into technical case studies for redesign. By the 1970s, modern arming devices included multiple redundant interlocks, coded switches, and two-person authentication systems to prevent accidental activation. Yet for every improvement, the old weapons remained, hundreds stored, transported, and maintained by human hands under the pressure of perpetual readiness. In official summaries, accidents were quantified as 1 in a million events, but each statistic carried lives, places, and near-catastrophic outcomes behind its number. The Goldsboro file remains the most chilling. A declassified drawing shows a 6-step arming diagram with 5 indicators marked completed in red pencil. At the bottom of the page, a handwritten note reads, "One simple, low-voltage switch prevented the collapse of the eastern United States." That sentence became legend among nuclear safety engineers, a reminder that the greatest risk often hides in the smallest component. Today, the buried bomb still lies beneath North Carolina soil, sealed under farmland, its exact position recorded in a restricted coordinate archive. Groundwater tests remain part of annual monitoring, confirming trace radiation levels consistent with buried non-critical material. The site is quiet, no monument, no museum, only cornfields, wind, and the memory of how close technology came to undoing its creators. In historical terms, the Goldsboro Incident defined the boundary between control and chaos, a day when America nearly erased itself not by enemy design, but by its own engineering. On February 5, 1958, a U.S. Air Force B-47 bomber collided midair with an F-86 fighter during a night training mission off the coast of Savannah, Georgia. The bomber, under call sign Ivory 2, carried a 7,600-pound Mark 15 Mod 0 hydrogen bomb armed with conventional explosives and uranium components. After the collision, the bomber's right wing was damaged, fuel leaked rapidly, and the crew received orders to jettison the weapon before attempting an emergency landing. At 7,200 feet over Wassaw Sound, the crew released the bomb to prevent explosion on impact. The weapon fell into shallow water near Tybee Island and disappeared instantly. Sonar and diver searches began within hours. Crews mapped a grid covering several square miles of marsh and sandbars, but found nothing except silt disturbances. Within days, recovery teams expanded operations using magnetic sensors and underwater cameras, documenting strong metallic returns but no visual confirmation. The Mark 15 was 11 feet long, encased in aluminum, and contained about 400 pounds of conventional explosives surrounding a uranium tamper. Official statements initially described the bomb as non-nuclear, claiming the plutonium pit had been removed for safety. Internal memos contradicted that assertion. Declassified letters from the Secretary of Defense in 1966 referenced a complete weapon, implying the Tybee device retained its full nuclear core. Environmental surveys through the 1960s detected no abnormal radiation in the area, yet warnings to avoid excavation or dredging persisted in Coast Guard advisories. In 2004, researchers from the Air Force and University of Georgia conducted renewed sonar mapping using modern side-scan equipment. They identified an anomaly consistent with a large metallic cylinder buried under 10 feet of sediment near the mouth of Wassaw Sound. The coordinates were classified to prevent public interference. Official reports stated, excavation could risk detonating residual explosives within the weapon casing. Fishermen in nearby channels reported strong magnetic interference on equipment, leading to speculation the bomb lay deeper than previously modeled. Residents of Tybee Island occasionally discovered fragments of aircraft aluminum, mistaken for parts of the missing weapon but traced to unrelated wrecks. The bomb remains designated as a lost device under Air Force Accident Record 4245. The file includes sonar imagery, environmental logs, and hazard assessments. Estimates suggest recovery would require dredging thousands of tons of sand, potentially releasing trapped methane and destabilizing the coastal seabed. Environmental experts argue that after decades underwater, the high explosive components likely degraded into inert compounds, reducing immediate risk. Still, simulations indicate even a non-nuclear detonation could produce a localized blast equivalent to several tons of TNT, dangerous to nearby communities. In 2015, a Freedom of Information release disclosed previously unseen photographs of the 1958 search vessels and naval charts annotated possible impact zone. The U.S. Army Corps of Engineers continues periodic monitoring, testing sediment for radiation or chemical traces as part of the routine environmental safety program. Reports describe the Tybee bomb as stable, unrecovered, and unlikely to pose critical threat unless disturbed, a cautious bureaucratic phrasing for an enduring mystery. Local historians maintain archives of newspaper clippings, interviews, and letters from crewmen who flew the mission and later retired near Savannah. Major Howard Richardson, the B-47 pilot, received the Distinguished Flying Cross for safely landing his crippled aircraft after releasing the weapon. He confirmed decades later that the bomb was fully assembled when jettisoned, contradicting the official claim of a dummy core. This contradiction remains unresolved, dividing experts between those who believe the device inert and those who warn of hidden fissile material. Tybee Island today hosts tourists unaware of the buried ordnance. Beach homes and marinas stand above waters where one of history's most valuable weapons vanished. No memorial marks the event, only a line in an accident log and a quiet policy note. Area remains under observation, recovery not advised. The sea covers the evidence, sand shifting with tides, concealing a relic of the atomic age that turned routine flight into a permanent question beneath the waves. Every year, ocean currents redraw the map, moving sediment, erasing sonar echoes, and reminding researchers that certainty fades faster than steel corrodes in salt water. The Tybee bomb endures as both artifact and warning, a weapon without a war, a reminder that even controlled power once lost can never be truly forgotten. On January 17, 1966, a U.S. Air Force B-52 Stratofortress departed from Seymour Johnson Air Force Base for a routine Chrome Dome mission carrying 4 hydrogen bombs. Over the coast of southern Spain, it rendezvoused with a KC-135 tanker to refuel in flight. The maneuver was standard, but required millimeter-precise alignment at 31,000 feet. At 10:22 a.m., the B-52 rose too quickly, striking the tanker's refueling boom. Fuel ignited instantly, turning both aircraft into a fireball visible from the villages below. 7 airmen died in seconds. The bomber's 4 Mk-28 hydrogen bombs broke loose and fell toward the fishing village of Palomares and the Mediterranean Sea. 2 bombs detonated their conventional explosives, on impact with the ground, scattering plutonium particles across tomato fields and olive groves. 1 bomb landed intact near a dry riverbed. The 4th plunged into the sea and vanished beneath hundreds of feet of water. Within hours, Spanish authorities sealed off the area while U.S. recovery teams arrived under Operation Moist Mop, a joint cleanup and search initiative. Soldiers in protective gear scraped away contaminated topsoil, packing 5,000 steel barrels for shipment to South Carolina for safe storage. Air samples and blood tests from villagers showed no acute injury, yet the political damage was immediate as Spain demanded public assurances and compensation. Meanwhile, Navy submarines and deep-sea drones combed the Mediterranean, using sonar and magnetic gradiometers to locate the missing bomb. Weeks passed as currents shifted the search grid. The U.S. deployed the submersible Alvin Asterisk, famous later for Titanic exploration, to descend below 2,500 feet. On March 17, after 80 days underwater, operators spotted a metal object resting on the seafloor and confirmed it as the lost nuclear device. It was hoisted carefully with balloon lines and winches, emerging coated in silt and seaweed under floodlights that illuminated history's most delicate salvage. Television crews filmed the operation. The image of the rust-streaked bomb suspended over the deck became an icon of Cold War anxiety and technological fragility. Declassified data later confirmed that none of the 4 weapons approached nuclear yield, though their explosive power in fully armed state exceeded 1.5 megaton each. The cleanup continued for months, with engineers mapping plutonium hot spots using portable radiometers and covering soil with plastic sheets to limit wind spread. By April 1966, soil radiation levels dropped below safety thresholds. Nevertheless, Spain retained ownership of the affected land pending further remediation. Negotiations led to the construction of monitoring facilities still active today, analyzing groundwater and airborne dust for trace isotopes. In the 1970s, reports revealed elevated readings in some plots, prompting joint U.S.-Spanish agreements to remove additional soil in subsequent decades. Satellite imagery from modern surveys shows agricultural recovery complete, but restricted zones remain fenced with signs marked Peligro Radioactivo. Culturally, Palomares became synonymous with both disaster and resilience. Locals replanted fields and hosted commemorations for lost airmen each January. The event transformed U.S. nuclear policy, forcing the end of airborne alert missions in European airspace and leading to new transport restrictions. Documents from 1967 show Pentagon directives mandating dual authorization for flights carrying live weapons over foreign territory. Scientists studying the Palomares cleanup call it a case study in containment, a rare example of rapid international coordination under nuclear emergency. Still, lingering debris beneath plowed fields serves as a quiet reminder of how thin the margin was between routine operation and irreversible contamination. The incident's archives fill thousands of pages, maps, soil charts, dosimeter logs, all bearing the same heading, Nuclear Ordnance Recovery PALOMARES. Every entry is written in measured language, but between those lines resides a lesson etched by fire and wind. Containment is never absolute, only continuous. On January 21, 1968, a U.S. Air Force B-52G bomber carrying 4 hydrogen bombs crashed near Thule Air Base in northwestern Greenland, scattering radioactive debris across the polar ice. The aircraft, part of Operation Chrome Dome, had departed from Plattsburgh, New York, for an airborne alert patrol over the Arctic when a cabin fire broke out mid-flight. At 39,000 feet, the crew attempted emergency procedures as dense smoke filled the cockpit. Losing control, they were forced to abandon the aircraft in sub-zero darkness. 6 of the 7 airmen ejected successfully. One perished as the bomber struck the ice-covered bay 12 kilometers from Thule, detonating its conventional explosives. The resulting fire vaporized sections of the fuselage and dispersed plutonium dust into snow and seawater, forming a contamination zone that spanned 3 square miles. Within hours, U.S. and Danish teams launched Operation Crested Ice Asterisk, a massive cleanup effort combining radiation detection, excavation, and ice cutting under 24-hour darkness. Over 700 personnel worked through polar night, cutting contaminated snow blocks, sealing them in steel drums, and shipping them to the United States for disposal. Radiation monitors recorded fluctuating readings as wind carried fine particles across the frozen bay, embedding traces deep within the ice sheet. Engineers used Geiger counters, remote drills, and flamethrowers to melt ice around the impact craters, exposing fragments of aluminum, wiring, and twisted bomb casing. The extreme cold turned every movement hazardous. Metal froze to gloves, and instruments malfunctioned under degrees C conditions, delaying progress. By April 1968, cleanup teams reported recovering roughly 85% of contaminated material, but the primary uranium components remained missing beneath shifting ice. Subsequent sonar surveys located metallic echoes below the surface of North Star Bay. Further dives were deemed too dangerous due to unstable sea ice and cost constraints. In declassified 1987 memos, Danish officials confirmed residual materials unrecovered, though radiation levels in surface ice returned to near background values within years. Local Greenlandic workers known as Thulemen later reported chronic illness and sought recognition for radiation exposure, leading to prolonged legal battles. The Danish government conducted health studies that acknowledged limited contamination, but denied causal links to specific medical conditions. Diplomatic records show quiet tension between Copenhagen and Washington, as public awareness of the incident grew during anti-nuclear protests in the 1980s. Satellite imagery decades later revealed subtle melt zones at the crash site, prompting renewed environmental sampling in 2008 and 2015. Analyses detected microscopic plutonium traces, measured in trillionths of a gram, confirming persistence despite 5 decades of snow accumulation. Researchers classified Thule as a legacy site, requiring periodic monitoring to ensure melting glaciers do not release deeper embedded materials. The crash accelerated policy reform. By mid-1968, the United States ended airborne nuclear alert missions permanently, citing intolerable cumulative risk. The Thule report concluded that the probability of accidental detonation remained low, but environmental consequences of dispersal were unacceptable. Archival photographs show personnel in white parkas against blackened snow, the juxtaposition of purity and contamination etched in monochrome film. Technical diagrams mark recovered fragments labeled primary housing, neutron reflector, and wiring harness, artifacts of technology scattered by cold and velocity. Modern environmental scientists consider Thule an inflection point, the moment military logistics acknowledged ecological boundaries under atomic policy. The site, frozen yet alive with invisible isotopes, stands as both memorial and laboratory, where each snow layer archives the memory of human precision and failure. Visitors to Thule today see no wreckage, only windswept ice and warning markers, but beneath the frozen surface lies a lesson. Control is not permanent, only temporary. Every winter, radar operators and maintenance crews still glance toward the bay, knowing the data beneath their screens began with a single spark in 1968's darkness. During the 1960s, the United States Air Force maintained a constant nuclear presence in the sky under a program known as Operation Chrome Dome. Its purpose was deterrence, armed B-52 bombers circling near Soviet borders, ready to retaliate instantly in the event of a nuclear strike. At the height of the Cold War, up to 12 bombers were airborne at all times, each carrying thermonuclear weapons ranging from 1 to 9 megatons. Flight paths covered the Arctic Circle, the Mediterranean, and the Pacific. Refueling tankers extended mission duration to more than 24 hours. Crews lived on alert rotations, sleeping beside the runway, trained to scramble and ascend within 15 minutes of receiving coded orders. The policy created near-permanent risk, combining fatigue, weather, and mechanical stress with warheads capable of erasing cities. Maintenance logs show aircraft completed over 5,000 Chrome Dome sorties between 1960 and 1968, accumulating millions of flight hours. Each mission required mid-air refueling, often multiple times, with heavy turbulence and jet stream crosswinds increasing collision probability. Investigators later noted that 3 of the 4 major Broken Arrow incidents, Goldsboro, Palomares, and Thule, occurred during Chrome Dome operations. The Strategic Air Command accepted the danger as necessary, defining acceptable loss as statistical inevitability within operational readiness doctrine. Pilots described constant pressure, icy cockpits, and sleep deprivation. Mechanical failure was feared less than simple human error during long shifts. Accident analysis showed that flight hours alone correlated directly with incident probability, yet command structure resisted grounding missions. Internal memoranda revealed concern from safety engineers. One 1966 report warned, "Continuous airborne alert creates cumulative exposure to non-recoverable failure." Despite warnings, strategic logic demanded visibility. Keeping bombers aloft signaled strength and deterrence against Soviet first strike capability. The cost in near misses was extraordinary. Fuel leaks, electrical shorts, and navigation failures filled daily logs, many never publicized. In 1967, Congress requested a classified review on risk equivalence, comparing deterrence value to catastrophic potential. The resulting report remains partially redacted. By early 1968, after Thule's crash, political consensus shifted. President Lyndon Johnson approved termination of 24-hour airborne nuclear patrols. The order marked the end of an era, the first acknowledgement that constant readiness was indistinguishable from perpetual hazard. Declassified flight manuals detail emergency procedures involving live warheads, jettison commands, arming plug removal, and deliberate sea impact coordinates. Each line reads as both technical instruction and confession of fear, protocols written for acts no one wished to execute. Following Chrome Dome's suspension, Strategic Air Command transitioned to ground-based alert, storing weapons in hardened silos and underground vaults. New protocols introduced redundant locking mechanisms, environmental sensors, and automated logging systems to reduce dependence on human oversight. The program's termination drastically lowered accident frequency, but left a legacy of contaminated sites, unrecovered ordnance, and decades of classified studies. Historians describe Chrome Dome as nuclear roulette in the stratosphere, a period when deterrence depended on continuous flight rather than stability. Veteran pilots recall both pride and fatigue, the sense of holding civilization between altimeter readings and radio codes that never came. Archival footage of these missions, contrails crossing polar skies, remains haunting, images of safety built on motion, of peace sustained by peril. Today, museums display B-52 models and declassified checklists under glass, silent reminders that deterrence once meant living in the air, waiting for a signal never sent. Every flight was a countdown extended indefinitely, and every landing a narrow escape from an apocalypse designed by its own guardians. Not every nuclear incident during the Cold War made headlines. Many occurred quietly across rural America, recorded only in declassified maintenance logs decades later. On March 11, 1958, in Florence, South Carolina, a B-47 bomber accidentally dropped a Mark VI nuclear bomb after its release mechanism malfunctioned during approach to an airbase. The weapon struck a backyard, detonating its conventional explosives and creating a crater 35 feet wide, flattening a farmhouse and injuring 6 civilians. Although no nuclear chain reaction occurred, the explosion scattered debris across hundreds of yards, reminding officials that safe systems could fail within routine procedure. Investigators recovered fragments of casing, fins, and wiring, all logged under Air Force Incident File 341, labeled simply accidental release, no yield. Photographs show children standing near the crater's edge, unaware they were meters from the remains of a live atomic weapon designed for intercontinental delivery. Local newspapers initially referred to the event as a jet explosion, until declassification years later confirmed it as an accidental nuclear drop. 2 years later, another crash occurred near Mars Bluff, also in South Carolina, where a B-47 again released a bomb unintentionally while conducting navigation training. The device's conventional charge exploded, demolishing a house and scattering shrapnel into pine woods. No fatalities occurred, but shockwaves were felt miles away. Government representatives compensated residents modestly, citing property damage due to military operations, omitting reference to the nuclear component. These cases shared a common pattern: ordinary flight errors transformed into near disasters because of procedural shortcuts and outdated mechanical systems. In January 1964, a B-52 carrying 2 thermonuclear bombs crashed near Yuba City, California, after structural failure in turbulent weather. Search teams located both weapons intact among orchard fields, their parachutes deployed properly, preventing detonation and minimizing contamination. Reports praised design improvements, but quietly acknowledged that a minor short circuit in the arming circuit could have armed both devices. The crew's quick response prevented ignition, yet internal assessments recommended grounding certain aircraft until electrical inspections were standardized. Between 1950 and 1980, the Department of Defense documented 32 incidents involving nuclear weapons, 12 within U.S. borders. Official summaries classified these as broken arrows, avoiding direct mention of how close each came to mass casualty scenarios. From 1965 onward, new interlocks and permissive action links reduced arming probability by magnitudes, but human error remained the dominant variable. In 1980, the Damascus, Arkansas incident reinforced this lesson, when a Titan II missile exploded after a technician dropped a wrench socket onto its fuel tank. The resulting blast destroyed the silo, killing 1 airman and hurling the 9 megaton warhead hundreds of feet away. It landed intact without detonation. Recovery crews spent days stabilizing the weapon, working under extreme pressure and chemical fumes, sealing it before dawn to prevent further explosions. Congressional hearings afterward cited the event as proof that absolute safety is unattainable when human oversight and high explosives coexist. These domestic accidents, while smaller in scale than international disasters, shaped internal safety doctrine and public perception of nuclear stewardship. They also revealed how secrecy delayed accountability. Many residents affected by early incidents learned decades later what truly occurred in their towns. Even today, scattered across archives are photos labeled only by coordinates, showing barns, fields, and suburban streets that nearly became ground zero. Every event added a line to the growing catalog of caution, proof that the weapons built for ultimate defense carried within them the inevitability of human imperfection. Behind the statistics were farmers, firefighters, and families who looked up one night and saw fire descending, unaware that history hovered above them in metallic silence. After decades of secrecy, declassified records revealed the cumulative human and environmental toll of America's nuclear near-misses. Each Broken Arrow incident left behind not only debris but lingering questions: how much radioactive material remained, and what exposure meant for nearby residents. In Goldsboro, North Carolina, groundwater tests are still performed annually, though officials insist contamination levels are within safe limits. In Palomares, Spain, locals recall the men in suits and masks who arrived overnight, digging up red soil while jets circled above the coast. Despite international agreements, radiation monitors decades later detected cesium and plutonium traces in olive orchards and coastal dunes. At Thule, Greenland, shifting glaciers continue to unearth metallic fragments and altered snow layers, long after governments declared the site clean. Greenlandic workers who assisted the cleanup, many without proper protection, later suffered illnesses that fueled lawsuits for recognition and compensation. Danish archives document hundreds of testimonies describing blisters, chronic fatigue, and unexplained blood disorders among those deployed to the frozen crash site. In the US, victims of domestic accidents like Florence and Damascus were rarely told the true nature of their exposure or the materials handled in recovery. Documents labeled confidential, do not disclose, often remained sealed until the 1990s, long after witnesses had passed away. By the time public acknowledgement arrived, most affected communities had been rebuilt or forgotten, their history buried beneath new roads and fields. Environmental scientists estimate that minute traces of nuclear material persist across several American states, undetectable without specialized equipment. A 2013 Department of Energy report confirmed measurable isotopic residues near multiple historical crash sites, yet concluded that no remedial action is required. Such language reflected bureaucratic caution rather than reassurance, balancing technical safety with political avoidance of renewed public anxiety. For historians, the pattern was clear. Each crisis ended not with resolution, but with gradual assimilation into national memory as classified footnotes. The U.S. military's internal philosophy treated accidents as isolated mechanical failures, rather than systemic indicators of overextension. But the documents, thousands of pages now digitized, tell a different story. Human fatigue, design flaws, rushed schedules, and statistical complacency. One Air Force colonel described it candidly in a 1972 memo: "The system works until the day it doesn't. Our luck is not policy." That observation, buried among technical tables, summarized decades of near catastrophes avoided by fractions of a second and inches of wire. Environmental monitoring continues under discrete federal programs, testing soil, river sediment, and vegetation near sites once dismissed as decontaminated. Public access remains limited. Many coordinates of unrecovered ordnance are redacted even in Freedom of Information releases. Experts note that secrecy itself becomes part of safety. Concealment prevents scavenging, but erases accountability from collective awareness. In recent years, filmmakers and researchers have retraced these events, visiting crash zones and interviewing surviving crew members. Their testimonies are remarkably consistent: pride in service mixed with disbelief at how close the country came to self-destruction. A retired navigator recalled hearing the words "Broken Arrow" over the radio, realizing it meant they had almost triggered the weapon they were meant to protect. He said later, "We trained for the end of the world, but no one trained us for almost causing it ourselves." That sentiment encapsulates the paradox of the nuclear age, a civilization advanced enough to hold its fate in metal, yet fragile enough to lose it through routine error. Each site, Goldsboro's fields, Tybe's seabed, Palomares' farms, Thewel's ice, remains an invisible museum of near annihilation, preserved by accident and bureaucracy alike. They stand as coordinates of memory, reminding future generations that the gravest threats rarely come from enemies, but from the perfection we claim to control. By the late 1970s, investigators began compiling a comprehensive log of all recorded nuclear incidents, an effort that became known informally as *the Broken Arrow List*. This document, once classified top secret, restricted data, cataloged every event involving loss, damage, or accidental release of nuclear weapons worldwide. In total, the list contained 32 confirmed U.S. accidents, with nearly half occurring within American borders or Allied territories. Each entry included coordinates, weapon type, safety mechanism status, and outcome, whether recovered, detonated, or still missing. The earliest recorded incident dated back to February 13, 1950, when a B-36 bomber jettisoned its weapon into the Pacific near British Columbia. Others spanned continents: Greenland, Spain, Japan, the Philippines, and the Arctic Circle, all sites where routine flights crossed into the edge of catastrophe. For decades, these records remained buried within technical archives of the Defense Nuclear Agency, reviewed only by analysts studying system reliability. In 1981, journalist Howard Morland filed repeated Freedom of Information requests, revealing fragments of the Broken Arrow summary to the public for the first time. The disclosures shocked audiences unaccustomed to the scale of nuclear mishaps, prompting congressional hearings on accountability and safety oversight. Transcripts from those sessions read more like testimonies from disaster survivors than policy reviews, engineers describing melted relays, pilots recounting in-flight fires. A recurring theme emerged: redundancy was not immunity. Each safeguard could fail when combined with fatigue, weather, and human improvisation. Analysts estimated the statistical likelihood of a catastrophic detonation at 1 in a billion per flight, yet multiplied across thousands of missions, that risk became tangible. Charts attached to the hearings mapped a grim pattern: clusters of incidents aligned with major flight corridors between U.S. bases and European airspace. One senator remarked, "Our greatest enemy may not live across an ocean but reside within our procedures." The Department of Defense responded by launching the Nuclear Weapons Systems Safety Group, an independent advisory panel tasked with reviewing every deployment policy. Their findings in 1983 concluded that older weapons lacked mechanical interlocks sufficient to guarantee safe recovery after physical damage. That same year, technicians discovered corrosion on several decommissioned warheads stored in humid vaults, reigniting debate over long-term storage conditions. By 1985, the government initiated a modernization program to retrofit all active weapons with enhanced nuclear detonation safety ENS systems. New arming devices required multiple electrical codes, environmental signals, and human confirmations to align before activation. Yet experts warned that the psychological dimension of error, the momentary lapse or misunderstood command, remained impossible to eliminate entirely. Every improvement reduced risk but never reached zero, a reality quietly acknowledged in the classified addendum titled *Residual Probability*. Historians later compared the Broken Arrow catalog to an archaeological record of fear, each entry a fossil of a moment when control almost collapsed. Some incidents still remain partially censored, with redacted coordinates and missing serial numbers indicating locations deemed sensitive or unrecovered. Among them are reports from the Pacific, suggesting weapons lost at sea near Guam and Okinawa, their exact status presumed irretrievable. Oceanographers warn that corrosion over decades may expose fissile cores to seawater, though dispersion makes environmental impact negligible on a global scale. Nonetheless, the symbolic weight endures. thousands of tons of radioactive hardware resting on ocean floors, silent monuments to the limits of deterrence. The Broken Arrow list, once a secret index of failure, has become a reference for historians and policymakers studying how close the 20th century came to erasing itself. Each line, clinical and concise, conceals untold lives and near apocalypses, reminders that perfection, when armed, can only ever exist in theory. In the wake of repeated incidents, American engineers and defense scientists began an unprecedented redesign effort to rebuild the entire philosophy of nuclear safety. The project's guiding principle was simple yet profound. A nuclear weapon must never detonate except through a deliberate, authorized act of national command authority. Every subsystem, from electrical switches to environmental sensors, was re-examined to eliminate the possibility of accidental or unauthorized arming. The first major breakthrough came with the Asterisk Permissive Action Link, PAL, a coded electronic lock that required a specific multi-digit sequence to enable arming circuits. Installed across the arsenal during the late 1960s and 1970s, PALs effectively prevented field crews or rogue actors from activating a device without presidential authorization. The codes were stored under strict cryptographic control, distributed only through encrypted communication channels and subject to multi-person authentication. Each PAL system used logic gates and microswitches resistant to vibration, heat, and electromagnetic interference, designed to survive catastrophic crash conditions. Parallel to PALs, engineers developed environmental sensing devices ESDs, mechanical safeties that armed weapons only after detecting specific flight profiles. These sensors monitored acceleration, air pressure, and temperature, ensuring that detonation sequences could not begin unless a weapon had been dropped in combat conditions. Laboratories at Sandia and Los Alamos conducted exhaustive tests, shaking, burning, freezing, and submerging weapons to verify that fail-safe logic endured under every stress. Video footage from those trials shows scientists observing explosions through armored glass, timing milliseconds between impact and electrical pulse interruption. Even so, many legacy weapons from earlier decades remained in storage, lacking modern safeguards but too costly or politically sensitive to dismantle immediately. To address that risk, Congress authorized the Asterisk Stockpile Reliability Program, mandating continuous inspection and testing of every active or reserve warhead. Engineers tracked serial numbers, component lifetimes, and environmental exposure histories, creating databases that functioned as digital DNA for each weapon. This era also marked a cultural transformation within the defense complex. Safety was no longer a technical add-on, but the central design philosophy. Internal manuals replaced terms like fail-safe with fail-deadly safe, acknowledging that mechanical perfection meant little without procedural discipline. Military training incorporated new human factors research, addressing fatigue, communication, and cognitive load during alert missions and maintenance shifts. By the late 1980s, simulation centers allowed crews to rehearse accident scenarios with deactivated systems, recording decision patterns for later analysis. Yet even with these advances, experts recognized the paradox. As systems grew safer, their complexity increased, creating new modes of potential failure. Dr. Sidney Drell, a physicist advising the Pentagon, summarized it in one sentence: "We can make it safer, but we can never make it impossible." The U.S. eventually expanded safety cooperation to include NATO allies, standardizing procedures for handling, transport, and emergency recovery. Joint exercises simulated lost weapons in desert and ocean conditions, testing coordination between nations under realistic time pressure. Each drill ended with the same reminder: zero accidents is not a goal, it is a process. In the early 1990s, after the Cold War, declassified summaries confirmed that no nuclear weapon had ever detonated accidentally in U.S. history. But those same documents quietly listed over 1,000 safety violations that could have escalated into major disasters had one switch, wire, or human decision differed. The engineering triumph lay not in perfect control, but in continuous learning, a system evolving through its own near tragedies. Every layer of modern safety, from coded locks to inertial sensors, carries within it the memory of Goldsboro, Tybee, Palomares, and Thule. These mechanisms are not merely circuits and metal. They are confessions in hardware, each one built to ensure that the same error never happens twice. By the dawn of the 21st century, America's nuclear arsenal had evolved from mechanical complexity into digital precision, its history written in accidents, reforms, and lessons. Declassified reports reveal a paradoxical achievement. The country that came closest to annihilating itself had also become the global authority on preventing it. Modern command and control systems now rely on encrypted satellite links, biometric authentication, and quantum-hardened communication relays. Each launch facility operates under two-person integrity, requiring simultaneous verification across independent systems before any armed command can execute. Every weapon, even during maintenance, is monitored by telemetry nodes that record temperature, humidity, and motion, transmitting data to national security networks. This architecture ensures that the slightest anomaly triggers alarms from field bases to Washington within seconds, a digital reflex built on decades of human error. Yet the legacy of the broken arrows endures, not as fear, but as institutional memory woven into every protocol, checklist, and sensor calibration. Historians note that no major nuclear accident has occurred on U.S. soil since the 1980 Damascus explosion, an unprecedented record born from past near misses. Still, remnants of the older world remain: the Tybee bomb buried beneath the Atlantic, the Goldsboro weapon sealed under farmland, fragments frozen in Greenland's ice. Each relic is an unintentional monument, a reminder that technology cannot forget, only conceal, and that safety depends on vigilance more than machinery. Government archives house thousands of pages stamped formerly restricted data asterisk, filled with coordinates, telemetry logs, and handwritten corrections by engineers long gone. Among them lies the understated phrase repeated across decades: system performed as designed, catastrophe narrowly avoided. That simple note, written after every crisis, captures the precarious balance between design and destiny, control and chance. Modern scientists studying those archives describe the Cold War not only as a geopolitical era, but as a continuous engineering experiment in survival. The weapons were symbols of deterrence, yet their management became an endurance test of human responsibility stretched across generations. Every safeguard, every circuit, every redundant lock represented an apology in advance, a recognition that fallibility was permanent. The American experience proved that catastrophe often hides within routine: a missing wrench, a misread gauge, a leaking fuel line in an ordinary morning sky. What prevented disaster was not perfection, but reaction, crews, scientists, and policymakers adapting faster than failure could unfold. In training academies today, young officers study these incidents not as relics, but as warnings written in steel, ice, and ocean sand. Simulations of Goldsboro and Palomares run on modern computers, teaching that prevention begins where certainty ends. The story of America's near self-destruction thus becomes something larger, a chronicle of persistence, the refusal to let error define destiny. Across the decades, fields regrew, oceans calmed, and skies cleared. But beneath that calm lies a network of memory coded in invisible vigilance. Every hum of a monitoring system, every green light in a control room, carries within it the echo of a moment when that light almost turned red. The broken arrows were not failures of technology alone. They were mirrors reflecting humanity's fragile control over the forces it created. And so the nation that nearly erased itself became the keeper of its own caution, standing guard over the line between knowledge and consequence. No memorial marks the exact spot of America's narrowest escapes. The monuments are hidden in procedures, in silence, and in the knowledge that luck has limits. The lesson endures in classified files and open skies alike. The greatest weapon is control, and the greatest danger is believing control will never slip again. Every engineer, every pilot, every policymaker who reads the archives knows the same truth, that history's survival sometimes rests on a single unbroken switch. The day America almost nuked itself did not end in fire, but in understanding, a fragile peace held together by vigilance, humility, and the memory of what nearly was.